Yeah, we figured, Robert gets invited all over the world to give keynotes on this stuff, so why not just have him give a keynote here, seems like, or at least a 20-minute talk. I appreciate that you stuck to your time limits there. So I'd now like to invite Robert back up as MC to introduce the next speaker.
Okay, so I'm back now, not as a proponent of millimeter wave, but as a UT faculty member who is co-organizing a conference here. So I'd like to introduce our next speaker, Anthony Soong. Anthony is, I've actually known him for, I think we met at, I want to say in VTC in Melbourne in 2000 something here, quite a while ago, and we've actually had a lot of collaboration since then. He's funded my group. We've written several papers together, one that got Best Paper Award. Anthony received his PhD from Alberta. Where is Anthony? Okay, he's coming down here. All right. And is an IEEE fellow, winner of several Best Paper Awards, has been heavily involved in standardization. And there was, I think, at one point where he was telling me he was gone 27 weeks or something out of the whole year, which doesn't give him a lot of time to admire his extremely fancy limited edition Corvette that stays in his garage and never leaves it. So, Anthony, what's that? Ortoglow, yeah, I mean, believe it or not, yesterday he actually had the long pants on. So, Anthony, we have had you speak many times, and you always have a lot of insight here, but we want to remind you that you have to try to go through all your slides and stick within the time limit. Oh boy. Yeah, I know it's going to be tough here, but yeah, we're looking forward to your insight here on the killer app for NFV. All right, so welcome Anthony here.
Thank you, Robert. It's getting close to 10 years since we started collaborating and funding the work. And I have to say, it's always been enjoyable collaboration there, so thank you very much. Now to his students, I noticed he had this little buzzer in his slide, so does he buzz you when you don't get the questions right in his class?
That's an awesome idea.
All right, so we're going to change the topic quite a bit, if I can only figure out how to make this work. All right, now I went twice. Okay, so some introductory slides, which I don't have to do any discussion of anymore, because Gerhard did such a good job of telling you why you need 5G and why we need to change the 5G network. So no more of that. 5G vision, Gerhard already talked about the entire requirement set that is very large. So no more of that. So we can distill this into some use cases. The one thing that I hear a lot when I go to different conferences about 5G is everybody talking about air interface. But this morning there was one person, the very first person, that came and talked, and he's an analyst, who said 5G is not likely to be about the air interface. Well, I don't know if I agree with that, but what I will say is no one talks about the network that will support the 5G and how to build that thing, so we're going to talk about that. So because Robert says, you being an air interface person, you can't talk about anything about your group that's doing in the air interface. So here we are. All right, so we distilled the requirements in a number of use cases. The first one came from NGNM. You can dig it up in the NGNM white paper, and it boils down to what Gerhard said this morning. You don't have to support all the requirements all the time. Therefore, what I can do is I can support some of the requirements for the right use cases at the right time. What that means from a network point of view is I'm going to slice that network so I can build a slice of the network that is dedicated to your service that will best optimize the first service for you. Okay, I can do that. But what that means is that I have to build a very flexible network. So there's three basic things here. We can slice it and have a centralized plus distributed network. We can have it fully distributed or fully centralized network. So I'm going to go very fast through this. So this just means that I have to have multiple slices and design a network that will do that. All right, next thing, Gerhard already touched on that too. So Gerhard has taken all my presentation, and I don't need to do much work here. He already says that you got to do cloud computing. Okay, I need to design a network that will do that. All right, here is something that's happening that, like what Gerhard said about latency, is happening that's a little bit unbeknown to us, and that is consolidation of data center and flatter networks. So we already see internet peering out in the internet world, especially in the tier 2 and tier 3. They're doing peer-to-peer. And then on top of that, what we have in the data centers for carriers is that there is a consolidation of the fixed and mobile data centers. So there's data center consolidation and flatter network. Okay. Next thing is another part that Gerhard said, you don't have to support all of the requirement all the time. So you don't have to support mobility all the time either in the mobile network. Some application needs it, very high mobility, some does not. Some need it in active state, some needs it in sleep, non-active state. And here's another one. This is a slide that I built. It actually touches on what Gerhard said this morning. We always been talking about that data is exploding, and that's true. I'm not arguing that part at all. Data is exploding. But then we plot the diameter data that we get in the network. That's down here on the bottom there. That too is exploding. So I put it all into one chart for you. If you look at the explosion of control signaling versus the explosion of data, control signaling is growing much faster. That does not mean control signaling is greater than your actual user data. It just means the rate of growth is higher. Okay, I heard an echo, but clearly it's an echo. All right, but there's also another aspect of it that's coming. That other aspect is data analytics. There's a huge group here in UT that does data analytics, and my belief is that data analytics allows us to expose the network to the applications, and that explosion of the that exposure of data analytics will even generate even more control data. So actually, the control data will probably likely grow faster than I even propose here. So what that means is that I need to really design a network that can handle not only massive data increase, but even much more massive control signaling. Okay. Luckily, we have new technology. That's why we're here, to help us solve this problem. Okay. The IT guys, Amazon and Google, they've been off building their thing. They build an IT cloud, nice and wonderful. And actually, the mobile world is starting to adopt this. So we have certain technology, NFV, which is the network function virtualization. What that means is that we run our network functions on just generic machines, no longer on dedicated boxes. Okay, and then we also have SDN, software-defined networking. Some people define software-defined networking as separation of control plane and user plane. That is true. There is that separation. I like to look at it. It allows me to connect my network very dynamically and flexibly. I won't spend much time giving you the whole details on why this is great. You can find that out from the NFV ISG. Just go to etsy.org and you can get their white paper. They'll go into deep details. I did that at GlobeCom, so I didn't want to repeat it here. All right, the next thing that we need is a distributed data plane, and we'll explain why you need a distributed data plane in a little bit. So what we want to do is take this carrier, that IT cloud that the Googles and Amazon's been building, and try to put it into some sort of a carrier cloud. So cloudification will happen. How's my time going? Oh yeah, I can make it. Okay, so what we want to do is put this next generation mobile core on top of generic hardware with software-defined connections, let's say. All right, in order for me to do that, I have to meet certain latency requirements. Gerhard tells me I need to meet 1 millisecond latency requirements. That immediately says it's pretty well accepted now that there is no way I can do this in a centralized network. Absolutely no way. So that means I have to have a flexible network, and if this green button works, yes it does. It's a flexible mobile core that allows me to have some flexibility in the 3 slices. I can have centralized and distributed user and control planes, dedicated function at the cloud edge. Gerhard already explained why we need that. And you can have centralized control plane and distributed user plane. We drew an example over here where we have some centralized network function, some distributed network function. So this is something you can think of the order of maybe in a nation you have one of this, and then this is of the order of maybe a small area, small community, not quite as large as Austin, maybe as large as Plano. All right, so and here, down here, we have the service-oriented RAN controller, which controls the actual radio network. We have communication switching fabrics that's in here. Okay, that diagram is easy to draw. The work for you guys. The researcher is to figure out, what to put here and what to put here. Not so simple. Let's say we want to do this, okay? Then you need a mobile core data service. So you need some sort of data tier, because I now have a mobile core that's tier. I need some sort of data tier. I need to change my session and mobility management, mainly because not all things need it. I don't need a full MME, for example, for an IoT sensor that doesn't move. And then I need a new transport plane here. I need to be able to do white box traffic forwarding, but it has to have stateful functions, a handle within the in-switch autonomous functions. Right now, the way we do things through here, right here, is through tunneling. Very bad, very bad. We need to change all that. In essence, this is because the core hasn't evolved for 20 years. All right. This is a picture to show you how multiple 5G slices can work concurrently. So we need to be able to design a network that does that. I can slice and dice dynamically, and maybe over here, I'm handling the short latency stuff that Gerhard needs, the 1 millisecond tactile stuff. Over here, I can handle the voice, which is of a lower latency. All right? On top of that, the other question we have to ask is, do we extend this down into the physical layer? We can actually take the concept of network slicing and slice it all the way down here, where we take the radio resources into the slice itself. Whether that is useful or not is actually an open question. That is an academic research question. All right. Here's another thing. We are talking about probably the most complex thing mankind has built, at least one of them, this communication network of the world. When we change the core, it is not going to happen overnight. Nobody's going to go in with a forklift, remove the core, and bring in another one. That just is not going to happen. So I would envision that we need coexistence of the 4G core. How we do that is actually an open question, but here's one way that we show an example of how we think it should be done, but it is going to happen that the 4G core and the 5G core must coexist, and I say it will probably coexist for at least 10 years, if not longer. So basically, in areas where you need the 5G services or need the 5G capability, you start deploying this core and you leave the rest with 4G. And then some of the centralized function can remain within the 4G core, like your policy and your authentication functions. Okay? All right. So does that mean I can just take this whole thing and put it on the Google Cloud? What do you guys think? Possible. The answer is not so fast. And here's the reason. We look at the cloud. Here's the IT, oops, come back. Here's the IT cloud with the data centers. It's actually, I think the IT guys did a really good job on the storage part and the computation part. What they have not done a lot of work on is the network part. And the reason is very simple. As far as they're concerned on the network, it's a wire. It's 10 to the minus 12 bit error rate. It's perfect. Well, in wireless world, what do we get? You remember? 10 to the minus 3, 10 to the minus 4? That's a 10 to the 9 difference. You know how big 10 to the 9 difference is? It's like the diameter of your hair compared to the diameter of the Earth. That's how big a difference there is. So in essence, what the IT core allows to do is it has few network abstraction, which is limited to ports. And if you look at it, what we need is better abstraction. And the other aspect is we cannot virtualize the entire mobile network. And there's another problem that we have. It's called RF. No matter what I do, I have to get real. I have to transmit this thing. I have to send it through the air, so I can't virtualize everything. All right, so let's take a look at what happens. So we drew for you, here's the right button, IT Cloud Data Center. Here's some carrier cloud data center with some carrier cloudlets, kind of the edge computing that Gerhard is talking about. If you look at the carrier cloud, you actually have to go up. There's only a gateway up here. You can think of these as virtualized machines, by the way. These aren't real frames if you want to take a look at it that way. But I have to go up and down. This is not fast. You're better off not to go up into the structure here and go through the switching directly. So really what we need to do is we need to realize proper distribution of functions and resources and realize the gateway here in a much more distributed fashion. Now, there's another problem. I have cloudlets and cloud and actual main cloud. If I instantiate two OpenStack protocols here, right here and here, you can do it, but it's more than just a multi-site problem. You will not get the speed that you need if you try to do that. Okay, and the main reason there's a difference is that as far as the IT guys are concerned, the network is just a wire. For us, it is stateful. It has to keep states, it has to keep track of the mobile states information. That's the difference. So we need to not only realize states, we need to support a fast path so we can go like this, or just quickly through the cloudlets. Okay, you said 1 minute, Robert? How about this? So what I'm saying here is just the amount of work needed to put this thing on a cloud. It's a big research topic. And I have outlined the evolution of this. I think significant work is still needed to be done, both theoretically and for us in the industry, practically, to realize this. And this includes, the modeling of this theoretical work. Many of this stuff I don't know how to model. Take, for example, distributed resource allocation. That is not a well-understood problem. One last thing for you guys. I hinted at this because there's a state in there that we have in the mobile network. One of the biggest research problems, I think, is can we remove that state? Currently, the mobile core has the state because that's the way we design it. But can we redesign it such that it's stateless? And then we can use the Google Cloud directly. That is the real research problem, a big research problem. That's it. Question?
Maybe one question. Right here. A really naive question. Why do you want to use the cloud? I mean, if Moore's Law is working for making...
Because there's no more Moore's Law. Moore's Law has been dead since 2005.
We just heard this morning it wasn't.
Well, actually, Gerhard hits it and tells you why it's dead. And Farouk touched on it a little bit. If you look at the actual computer CPUs, if you notice, they don't run any faster anymore. You go into multi-core. And since 2005, because they went to multi-core, you see, along with Moore's Law, there was this savings of energy as you densify the chip. That saving of energy is gone. That's why Moore's Law is dead. Moore's himself says his law is dead. It's just not us. Yeah, so that's the argument of Moore's Law. But I'll give you a better reason why we want to go to the cloud. The reason we want to go to the cloud is because of scalability and the ability to create services much faster. Right now, it takes a carrier 18 months from the start to putting a service out on the real world for consumers. If you go through the cloud, the hope is to reduce that to weeks. And then we have a whole new model. Services are no longer going to be designed in a very, let's say, systematic fashion. We now adopt the app model that's in the tablets and so forth. What we will have is many people will develop apps for the services. We'll go throw it out because it takes only weeks to get it out on the real world. Evolution will take place, and the good ones will survive, bad ones will just go away.
All right. Let's thank Anthony again. I got the mic. All right, we're going to come back here at 3:15 after the break. Please be prompt because we have a talk by Ian Wong on waveforms for 5G.